I'm going to talk about triangulating manifolds, as Jean-Daniel mentioned. I just want to mention the co-authors that work with me on this. I'll mention briefly some work I did as a graduate student at SFU with Torsten Moeller and Richard Zhang. But the bulk of this work it's really joint work with Jean-Daniel, Arizet, and Matthijs. They're very much collaborators in all this. And some of this work was done up in Groningen with Matthijs' supervisor, Gert Vector, and I also worked with a student there, Nicolai. Okay, so I want to triangulate a manifold. And what do we want to do? We want to create a simplicial complex that's homeomorphic to the manifold, and we want to have an algorithm to do this. And we want to be able to have a metric on our complex as close to the metric on the manifold. So we're assuming we've got, say, a Riemannian manifold or some metric on the manifold. And we'd like to get an idea of how many points we need to achieve this, how dense the sampling should be. In terms of algorithmic realizability, we're interested in getting algorithms that don't have an exponential dependence on an ambient dimension if we happen to be working with a submanifold of Euclidean space. We really want to be focusing on the dimension of the manifold itself. So the work that showed that you could triangulate manifolds with Cairns and Whitehead, that's kind of in the spirit of what we were doing. They worked locally in coordinate charts, and this is the method we take. Whitney used his embedding theorem and made a complex by intersecting the manifold, the embedded submanifold, with the Cartesian grid. So this is similar to kind of things that are done in graphics. We use results that Whitney had, but that method really depends on the ambient dimension, so it's not the way we wanted to go. So we use Delaunay techniques, and I just want to really quickly go through. I'm sure everyone knows what it is, but just to give the perspective, here I want to talk about a Delaunay triangulation of the plane. I have points. I look at a Voronoi diagram, do a tessellation of that in terms of points that are closest to this site. And then we look at the nerve of that Voronoi diagram. So I'm making simplices whenever Voronoi cells mutually have a non-empty intersection. And generically, I get a triangulation. We think of this as an abstract simplicial complex that we can naturally embed into the Euclidean space. And the property of these Delaunay triangulations, this kind of characteristic property, is this empty circumball property. So the circumcenters of the triangles we get are at the Voronoi vertices. So the vertices of the simplex are the closest sites to that simplex, and the circumball is empty of all other sites. And this property characterizes the Delaunay triangulation. And so you have this issue of genericity. We look at this as an abstract simplicial complex, and we say if it's generic, it's a triangulation. Generic means that you only have m+1 sites on an empty ball. But m is the dimension of our space we're working on, and that's the only genericity assumption that we need. Modulo, we assume that the affine hull of our points occupies the entire space, but other than that, you don't have to worry about having too many points on smaller flats. This all gets picked up by the property that you don't have too many points on the empty balls. And so if you have this genericity property, you get a triangulation. This was Delaunay proved in 1934, and the proof is pretty simple. There's kind of two aspects. One, and they both rely on this empty ball property. One is if you have two Delaunay simplices, then in the embedding, in Euclidean space, if they intersect, they only intersect in a face. And so from our perspective, that's kind of an aspect of the embedding. But there's another aspect to the proof, is a topological condition on the complex itself. And this is what is interesting to us. So the fact is, if you have a face of a simplex, a Delaunay simplex of codimension 1, so if I'm in m-dimensional Euclidean space, I'm talking about an m simplex, m-1 simplex, it's defined by m points, then it always has two cofaces. It's always the face of two full-dimensional simplices, no more, no less. So I'm not considering boundaries here. We're going to be working on compact manifolds. Delaunay himself just assumed a periodic point set as if he was working on a flat torus. So we have no boundary, and therefore we have exactly two full-dimensional simplices are a face of every codimension 1 simplex. And this is a property of the intersection of spheres, if you will, in Euclidean space. So we'll just work in three-dimensional space here. I have 3 points. They define a triangle, a codimension 1 face. If I have any sphere that contains those points on the any sphere that contains those points, or any ball that contains them on the boundary, it has this circle, this unique circle defined by those 3 points. And if the two spheres intersect, they intersect exactly on that circle. And so this means that if you have 3 spheres that contain the same simplex, one of them is contained in the other 2 balls. And because of this, we can never get a third tetrahedron to be a face of this triangle. And I say never. The only way we could do it is if we put a fourth vertex exactly on that circle. And that's a case where it would be degenerate. So this property of an intersection of 3 spheres is important to us. So we're going to move from Euclidean space into surfaces. And there, when we're triangulating surfaces, Steve and Jean-Daniel observed that if you have, so they're using a metric of the ambient space just restricted to the surface, and they observed that for small enough balls, they have this pseudo-ball property, or the pseudo-disk property, which means if you're looking at the boundaries, they intersect the way Euclidean circles intersect. So either they intersect transversely twice, or tangentially once, or they don't intersect at all. And so in this two-dimensional domain, that suffices. If I have a codimension 1 simplex, which is defined by 2 vertices, and I have 3 circles that contain that, then I'm going to have this property that one of them has to be contained in the other 2. And so this pseudo-disk property gives us triangulation. And if we look at this, same thing happens if we're looking at intrinsic distances. So rather than measuring distance between points just as Euclidean distance, we measure in geodesic distances by lengths of curves on the surface. I'll give you a proof by pictures of how this pseudo-disk property works. But first I have to say what I mean by a small disk. And so I govern the size of my balls with what we call a sampling radius. It says no Delaunay ball can be bigger than this sampling radius. The sampling radius says, okay, it's a way of saying the density I need of points on the surface. And if I have pick any point on the surface, then the closest point in my sample set is going to be less than the sampling radius away. There's a convexity radius. A geodesic disk is not necessarily convex. And when I say convex, I mean I take any 2 points in that disk, there's a unique minimizing geodesic between them, and that geodesic is contained in the disk. And it's not true in general. You can even think of a cylinder. If you wrap it around too much, the geodesic wants to go outside. But if it's small enough, this is going to be true. And then there's the injectivity radius, which is looking at just radial geodesics emanating from the center. I just demand that they never intersect each other. So they're all like these spokes going out from the wheel don't intersect. And so I'm demanding that these sampling radius is going to push my balls to be smaller than half the injectivity radius at any point. And now we can see why they have to be pseudodisks. So first, we're going to look at tangential intersections. So I'm looking at the figure of the red and blue circles on the left there. And up at the top, I'm representing a tangential intersection, and there's a green line going through it. So what I want to say, we have to know there's this so-called Gauss lemma that says that a radial geodesic out to the geodesic sphere, it intersects that sphere perpendicularly. So the tangent vector to the geodesic is perpendicular to the tangent plane of the sphere at that point, or the circle in this case. And so if I've got a tangential intersection, that means those two geodesics emanating from the red dot and the blue dot, they line up exactly. And so the image of this is actually the trace of a single geodesic. So I've got a geodesic between these 2 points. They're within the injectivity radius of one of those points, because I've got a condition that I've got a half injectivity radius on my sampling radius. So that means that has to be the unique geodesic between the points. I can't have any other intersections in this case. If I have a tangential intersection where the tangent vectors have the opposite orientation, it has to be the only intersection between the disks. Now in the middle, we're looking at the other case of a tangential intersection where the two tangent vectors have the same orientation. And in this case, well, there's only one geodesic going out in a given direction. So both centers have to lie on this geodesic. That means we've got a relation between the radii of the disks. So the radius in this case of the blue disk is equal to the radius of the red disk plus the geodesic distance between the centers. And that has to be true everywhere. So if there were another intersection, you just draw a triangle there, but the triangle inequality in this case forces your triangle to be degenerate. These two centers always have to lie in the same geodesic, so the only way there could be another intersection is if the two disks coincide. And in the third case, I'm looking at transverse intersection. And here we want to claim that there's only two. So I'm looking at a red circle and the blue circle there on the outside. And what I do is I say, okay, look at the components of the red circle that lie within the blue ball. Just pick one and take the point closest to the center, to the blue center, and draw a line to it, and then create your smaller blue disk of that radius. It'll be tangent at that point, and because we already know that that point has to be the only intersection, what I've drawn is impossible. It means I have to have taken the closest component, but I just chose arbitrarily, so there can only be one component, so there can only be two intersection things. So we have that pseudo-disk criteria. The argument on the right is different from the one that was published. Matthijs pointed out there was an error in the published one. So this argument's slightly different, and didn't seem to use the convexity radius. Okay, so now we're going into higher dimensions. There is a problem now. So what I want to emphasize here is we, in 2 dimensions, we have this nice sampling criteria, I say if I make my point set dense enough, then I've got a triangulation. That's all I need. And this is kind of what we would love to have something like this. But in higher dimensions, it's not going to be that simple. And so one way of seeing this problem is that we don't have this property of three. Let's stick in dimension 3. 3 points don't define some kind of intrinsic circle in the three-dimensional Riemannian manifold. In other words, two spheres will intersect in a topological circle, but then I bring in a third sphere, it intersects in another circle. It leaves room, in this case, for the green ball that I had before that was completely contained. It can show a face somewhere, and I can actually put another vertex there, and I get a third tetrahedron on that face. This is kind of an almost degenerate configuration, but it's not really degenerate. And we looked into this obstruction. We looked at this in terms of the Voronoi diagram, and so I'll just briefly try and describe it here. This kind of obstruction was known for the ambient when you have a submanifold. Steve and Jean-Daniel had shown that you get these problems with the Delaunay triangulation. So the same problem shows up with the intrinsic metric, and in this case we've got a scale invariant obstruction. So I want to describe how it works. Imagine I've got a Riemannian metric. It would be Euclidean if that's the identity matrix. So I'm just in a coordinate patch in three-dimensional space. But here we've added a bump function to how things behave in the z direction, and that bump function depends on where you are in the y direction. So here on the two images up there, I'm looking at, on the left, at the Euclidean case. I'm looking at the slice, the y equals 0 plane, the xz plane. And I've got these 4 points. They're almost equidistant, but the u and v in the z direction are slightly closer together. But now when I apply my new metric, they're effectively further apart, and it changes the Voronoi diagram. But because this bump function tapers off as I go in the y direction, we get the same kind of, if we looked at slices further away from that plane on either side, it would be back to the Euclidean configuration. So what means we get a Voronoi vertex on either side. So we get a simplex with two Voronoi vertices. It's some obstruction. And the thing about this is it happens at all scales. So not only does it kind of throws away the hope of having a sampling density that'll work for all manifolds, but even if you say, okay, at that manifold, this doesn't work because of this obstruction, if you throw more points at it, this particular configuration is always there, no matter how dense you go. So you don't have a hope that asymptotically things will work out. And this bump function is benign. We don't need a compact sport. It could be analytic. Okay. So what we do to deal with this, now I'm back in Euclidean space. I look at my Delaunay balls, and I demand that they're protected. So not only do I not have too many points that are on the ball, but I demand there's a little bit of a buffer zone around it. There's a delta, some distance delta, and any other point that's going to be a vertex of a Delaunay simplex, it's got to be a distance delta away from my Delaunay ball, and then I say it's delta protected. And so if you can arrange to have all the m simplices in your Delaunay complex be delta protected, I like to say that is a delta generic configuration. We've parameterized the genericity a bit. Then you get some nice things happening. You've got the stability results. So we introduce a couple of parameters. T0 is a lower bound on the simplex quality. I'll talk about that next a little bit. And mu0 is kind of a separation parameter. So the longest edge to the shortest edge, or sorry, the shortest edge to the longest edge. This is a quantity less than 1. And with these with protection, then I get this stability with respect to perturbations of the point. I can wiggle the points a little bit, or I can even change the metric a little bit, proportional to my protection. And then assuming we have a sampling radius, we can talk about a bound on the quality also. It kind of depends on this square of this quantity. So I'm not going to go into simplex quality too much, but I want to really convey that this is a pretty central issue in triangulating manifolds, is quality of simplices in some form or other. We talk about thickness, so we're measuring the quality by just looking at the smallest altitude, and we normalize by the diameter of the simplex. We also divide by the dimension, because we thought that seemed like a good thing to do when we first did it. Okay, so this protection, achieving these delta protected point sets, or delta generic, we can do this, and there are already algorithms out there for trying to get Delaunay triangulations that have quality simplices, and these algorithms can be adapted to provide protection also. So you have the weighting one where you manipulate the metric using the Laguerre diagram instead of plain Voronoi diagram. Or you can use refinement, adding more points. What was interesting to us is perturbation. And that's because here you just work with the same number of points. You're using the same Euclidean metric. You just have to move the points around a little bit. The algorithm, and especially its analysis, was quite complicated, and we later, after we did a lot of this work, found that you get a much simpler analysis with this Moser-Tardif algorithm, that this algorithmic Lovis's lemma, local lemma. The protection provided is dependent. The exponent is the dimension squared. It was dimension cubed before. But I'm not going to talk about that, but just in reference to what we have done. Okay, so now we want to go to triangulating manifolds. And as I said, our approach is to work in the comfort of Euclidean space. We go in local coordinate neighborhoods, and we'll do our triangulations there, because here we have the protection, and we know if you take a small enough neighborhood, you can hope to have a coordinate chart that doesn't distort the metric so much. So our Delaunay triangulation, if it's protected in the coordinate chart, will be a Delaunay triangulation on the manifold. And when we're doing the perturbation algorithm, we have to, the perturbation algorithm works by just visiting each point only once. You never go back to the points. We have to be sure that, when we're doing something in this coordinate chart, we don't mess something up in the other coordinate chart. So algorithmically, what became important is the transition functions. In order to produce the complex, we didn't even need to look at the metric on the manifold or anything. We're really looking at the transition functions and how that's distorting distances. So the issue is that if you don't have protection, you're looking at one coordinate chart, you get a Delaunay triangulation, and you look in another, you're using kind of morally the same points, they're just in a different coordinate chart, so the metric's slightly different, you get a different Delaunay triangulation, and you get a conflict. And so what our stability result is a way of getting around that conflict. So here's kind of a preliminary result. I want to talk about distortion map. So I've got a C distortion map. If f is from one metric space to another, if it doesn't change distances very much, this is the first expression. If the distance between the 2 points before and after is not changed very much relative to the original distance. So C is going to be this important parameter for us. It's our metric distortion parameter, and it's going to have to be small. a mu epsilon net. This is just how our sampling criteria. We're going to demand that we have a sampling radius epsilon, and we need a sparsity condition, which will be mu naught epsilon, and that's a mu epsilon net. So now if we look in every coordinate chart, we have this mu epsilon net condition, and the epsilon actually can be local, specific to each coordinate chart. Then what we need, so the big thing that we need is this low distortion on the transition functions. So that at this time here, I'm not talking about what epsilon is. We just need, the important parameter here is the low distortion. And to get, generally to get low distortion, it means you need small coordinate charts. And we need to have epsilon small enough that we have enough points in that coordinate chart to make a local triangulation. So we have this dependence on the cube of the dimension. This is because this is a result that was before we discovered the Moser-Tardis algorithm. We have this perturbation parameter, which is smaller than the smallest distance between the points, and that's playing a role also. How much the points can move, but we have little disks around every site, and these disks don't intersect. So when we have these conditions, then we can say, okay. If I've got here I'm assuming I have a metric on the manifold, then I can talk about a Delaunay triangulation. So we're able to produce this complex without even mentioning the metric on the manifold, but to say it's a Delaunay complex, we need to actually demand that the coordinate chart itself has low metric distortion. That gives us low metric distortion on the transition functions also. And so here we've got it. We've got this manifold complex that we can call it a Delaunay complex, but we can't yet call it a Delaunay triangulation, because we have to be able to call it a triangulation, we have to show that this complex that we've built, which we built very naturally in coordinate patches, we have to show it's homeomorphic to the manifold. And this is kind of the technical thing that I'm going to talk about for the rest of this talk. How are we going to do that? So in this setting, when we were doing this, we were not looking specifically at a submanifold of Euclidean space. We're looking at an abstract manifold. So what is the map we should use? You know, how do we do it? And the idea is you'd think just patching together a natural map into your coordinate charts, but what comes out is there is this very natural definition of Riemannian simplices. You can define barycentric coordinates. If you have points on the manifold in a small enough neighborhood, I can define a map from a regular Euclidean simplex into the manifold, and I'll call the image of this map Riemannian simplex. So how does it work? We can look at this energy function, which is this sum of the square distances to the points. It's weighted by barycentric coordinates. And if you look at that in Euclidean space, if my manifold was flat, this gives me a convex function, and the minimum of that convex function is exactly the point with those barycentric coordinates. What Karcher showed in the 70s is that in a small enough neighborhood of a Riemannian manifold, this is also a convex function, and it's got a unique minimum. And so what small means here, we have to be smaller than half the injectivity radius, but also we've got this dependence on an upper bound on the curvatures, the sectional curvatures. And so so this is the map we use, and you go to point that minimizes that functional, and that defines my map. That defines my barycentric coordinates on the manifold. And so that works as long as you're in a small enough neighborhood. This map is well defined. But what we're interested in ultimately in getting to a homeomorphism. The first step, I need that this map embeds my simplex. I need that this is a diffeomorphism. And so we have this nice kind of characterization. So on a Riemannian manifold, there's this natural exponential map from the tangent space to the manifold. So if you like, it's like a natural coordinate chart. And if you lift up by the exponential map, you lift your points up, you get points in Euclidean space. And if you do that for any point in your Riemannian simplex, you lift up and you get a non-degenerate simplex, then this Riemannian simplex will be non-degenerate. And so building on that and the way, well, with a bit of work, you can give explicit criteria to show that when the Riemannian simplex will be non-degenerate. So the idea is it depends on the quality of the simplex, but we only talk about quality in Euclidean space, so you have to relate it to a Euclidean simplex. So what we would do is relate it to one of these lifted simplices in the tangent space. Or what I'm doing here, suggesting is you can define, given the geodesic edge lengths, you can define a Euclidean simplex with those edge lengths. Now, that's not always true. What you have to do is you have to look at the determinant of a matrix that essentially represents volume or volume squared. And if that's positive, then you have a Euclidean simplex. And if it's big enough, you've got a way of measuring quality of that abstract simplex. So this statement down below, if I have this Euclidean simplex made with the geodesic edge lengths, if its thickness is bigger than the square root of an absolute bound on the sectional curvatures, the bound on the absolute value of the sectional curvatures, times the edge lengths, the diameter, then this simplex will be non-degenerate. So we've got this, now we've got the condition to get the individual simplices embedded. And from that, we want to create a demonstration of when this map will be a homeomorphism. And I'm going to talk about that a bit more later, but next. But with this, once we've got that result, we've got this barycentric coordinate map, and we show it's a homeomorphism. Now I can talk about what our analog of a sampling condition is. So this is a Delaunay triangulation of a Riemannian manifold. We can say that we have this. If I have now I'm using the distances on the manifold itself, not on the coordinate charts. So I have a mu epsilon net, and epsilon has to be smaller than this bound. The important thing is the expression on the right in that minimum. We've got a bound on the absolute value of the sectional curvatures is playing a role. The next term, so although the simplex quality isn't explicitly stated here, that next term is coming from the perturbation algorithm to get the projection and the quality. That's where the m cubed is coming, which would have been m squared if we were using Mozart-Tardis, but we weren't then. And then times the perturbation parameter. So when we have this, when this sampling is this dense, then we can say, okay, we can produce a Delaunay triangulation. We've got it, enough quality. We can define a piecewise flat metric on that simplicial complex, and that metric is close to the metric on the manifold. So this is good, but yeah, in terms of sampling density condition. Yeah, the waters are muddy compared to the to the two-dimensional case. Okay, so now I want to talk about how do we show that the map is a homeomorphism. This proof I'm going to sketch out now is one that we produced after the Riemannian simplex paper, so it's simplified a bit and it's more general. The reason we went back and revisited this is because we wanted. So we had a proof of showing that the barycentric coordinate map is a homeomorphism, but now we were looking explicitly at submanifolds of Euclidean space, and in that context, the natural map to use is this closest point projection map. So you imagine you've got a submanifold in Euclidean space, and you've got your complex, which is hopefully embedded, but at least it has its vertices on the manifold. And so in a neighborhood of the manifold, there's a unique closest point for every point. So there's a natural map. It just takes you to the closest point on the manifold. And we want to show explicitly that map is a homeomorphism. It's a bit complicated with the proof we had in the barycentric coordinate case, and this is actually quite a bit simpler. Okay, so we're going to stick with our approach that we had before of working in coordinate charts. And now I've got two manifolds. I've got this simplicial complex that I've constructed and the actual manifold. And I've got this map. I don't need to specify what it is. We've got two candidates, the barycentric coordinate or the projection map. And I want to show it's a homeomorphism. So yeah, again, we're going to focus on a coordinate chart, but we want this compatible coordinate chart, and I'll talk about that next. So this proof, this argument that I'm going to give doesn't actually use differentiability at all, and I didn't mention it before, but our construction to actually produce the manifold complex, it didn't use differentiability either. The only candidate maps that we know, the barycentric coordinate map or the closest point projection map, we only know how to deal with them in the differentiable context. So, well, I'll talk about that a bit more later. Okay, so, but the outline of what the homeomorphism proof is kind of standard. It was a standard thing in graphics anyway. You want to show that this map's a covering map. You show it's a local homeomorphism. And then when you have that, you just need to show it's injective because we've got a compact manifold. So there's just those are the two big steps that we want to do. But I have to talk about these compatible atlases. And so this looks kind of messy, and when I talk about it, it sounds kind of contrived and complicated, but it's really, I'm just trying to formalize what we actually do. When we're constructing this manifold, we have these sample points on the manifold. We map into local coordinate charts and we triangulate there. And what this compatible coordinate charts is trying to express that condition. So what the condition is saying is I've got this map from H, from my simplicial complex to the manifold, and I have an atlas on the manifold, one coordinate chart for every sample point, every vertex of my complex, and I want a little complex in the big simplicial complex A. I want a little complex for every vertex that gets mapped into the coordinate chart on the manifold, and so I can bring that down to Euclidean space, and my coordinate chart for the simplicial complex is going to be the secant map of that map. So I'm looking at the lower line there, H composed with the the coordinate chart brings me into the Euclidean domain, and I just look at the vertices and connect them with straight lines, and I demand that this gives me a piecewise linear embedding of these local maps. And so what we're going to be focusing on is the resulting map, which is just a manifestation of our map H, this map that I want to show as a homeomorphism in this coordinate domain. I'm going to call it FP, and it's just what that map looks like in a local coordinate chart. So I've got the black complex here, which is a piecewise linear representation of my complex. It's been mapped into Euclidean space, and then this map FP is like I'm mapping it to the manifold. It's no longer linear, and this is the map we're going to analyze. And I'll put little hats just to distinguish points that I have in my abstract complex that will be mapped into the Euclidean space. Okay, so for the local homeomorphism proof, we base it on Whitney's lemma, which is saying if I satisfy two conditions, I've got this open set, and if that open set under the map, it doesn't conflict with the boundary of my complex, and I can find a point in the image of that open set that only has one point in the pre-image, then that space V, this subspace V, is embedded. And the space that we're going to look at is just a shrunken down version of we're going to take for our local patch a star of a point, and we're just going to look at all the points that have barycentric coordinates that are larger than n+1. We just look at the open neighborhood that contains that set. And so that'll be a cover of our whole complex, and if we show that these are embedded, then I've got that the map is H is a local homeomorphism. And the three ingredients that we need here, so we demand that FP is low distortion when restricted to any simplex, and then we have this trilateration result. This is, if you're in the plane and you know your distance to 3 points on a triangle, then you can tell where you are. And if there's some error in that, then you have you know where you are roughly. And that first expression up there is expressing this. And when I say roughly, it depends on the t in the denominator is the quality of your simplex. If you have a flat, crappy simplex, then your ability to localize yourself is reduced. We use the metric distortion to show that there's a point B. We just take the barycenter of the largest simplex, and the other thing is important is if I have a point in a star in the Euclidean, a full star in the Euclidean space, okay, then it can only be so far from the boundary. The next step is injectivity. I've run out of time, so I'm going to just quickly mention that if no vertex lands in a simplex, then we have injectivity. But this is a hard criteria for us to work with, so we instead look in the Euclidean space where we've just been built a Delaunay triangulation. We know it doesn't happen, and so we make that the condition that we need to have. No vertex lies in a simplex in your coordinate chart, and that works out that's enough because of our low metric distortion, and the barycentric boundary condition means that the barycentric coordinate, if there were a conflict point, it would have to have a small barycentric coordinate, and we can do that for every vertex of the simplex, and these barycentric coordinates should add to 1. Okay, so our final criteria has these 4 points. The vertex sanity is my injectivity criteria. I have the distortion I need on the local version of the map. Depends on the square of the simplex quality, and this bound on this sparsity bound. Okay. Well, the exploiting the differential. So in the Riemannian simplex, this is the last slide. The last one's a thank you. The Riemannian simplex homeomorphism proof had the same idea, but we embedded the whole stars and we used the differentiability of the map, and we bounded it against a linear isometry. The analysis is quite a bit more complicated, but you only have a linear dependence on the thickness. Yeah. Unfortunately, there was error in that paper on the injectivity was not properly done. So this is fixing that. Okay, and I guess in future work, simplex quality is really a key thing here. Siarge and Aruni have been looking at simplex quality in structured, like lattices and structured triangulations of Euclidean space, so we get some idea of what we can get in Euclidean space. And I think it would be interesting to look at more structured manifolds. Okay, thank you.